Okay, so I hope you had a good lunch, but this is not the time to sleep, so we're going to talk about event-driven architecture. So as our colleague, as my colleague introduced, like I'm Shafreen Anafar. I've been working for WSO2 for like 12 years now. I'm currently working as the Ballerina Lead. Okay, so before I start the presentation, I just want to do one clarification. So I'm wearing my presentation T-shirt, which says HTTP. So this stands for Hypertext Transfer Protocol, not anything else. Because in Sri Lanka, it seems there's another meaning. So based on the person, meaning could change. Okay, now that I have clarified that part, let me start with the agenda. So today we're going to talk about increasing demand for event-driven architecture. So what we are going to talk today is something like this. So we'll discuss about why, and then we'll discuss how we can solve that problem, and then we'll discuss what we get as a result. So under what, we'll be discussing about benefits, different shapes of event-driven architecture, and then a bit of expansion of event-driven architecture. So that is what we are going to talk today. So if you guys have any questions, feel free to interrupt me and ask. I would like to make it more like a discussion than a presentation. But since we only have 30 minutes, if you have too many questions, don't ask. You can ask after the presentation. Just kidding. Okay, let's start with the million-dollar question. So why? Why do we need event-driven architecture? So since we are talking about events, I thought we can start with the very first event of this universe, which is Big Bang. So Big Bang happened, and soon after that, universe went from something that we could hold in our palm to something so big within like not even seconds. And then it gave us 4 forces, and then it went on to create the stars, and stars created the solar systems, and the chain of events continues. So today we are at a point like, when we look at the sky, we can see like millions of stars. So by the way, this photo was taken at Yala. So if you go to Yala on a good day, you can actually point your camera to the nice sky and take a picture like this. So here you can see the Milky Way, and you can see the configurations I used in my camera to get this shot. So coming back to the topic today. So similarly, now we are at a point where we have like, millions of computers. So these white dots are representing those computers. So what if we can, make these computers collaborate? If so, we can do like, amazing things. Just like, humans collaborate, the outcome is quite huge. So we discussed this a bit during previous sessions as well. So that's why we say like, when people collaborate, 1 + 1 is not equals to. It is way more than that. So similarly, we just want to model the same thing for computers. So then the question is about, how we can make computers collaborate with each other. So when it comes to collaboration, the main thing that is needed is a way to communicate. So that's why, when we humans collaborate, we have different languages. So similarly, we need a way to make computers communicate with each other. So then comes the next question. So how are we going to make computers collaborate with each other using different style of communication? So if you take 2 computers, now we need to figure out a way to make them communicate with each other so that computers can collaborate and do amazing things. So when it comes to communication, there are actually two ways to do the communication. One is request-response style communication, which is quite common. The quite common protocol we use for this style of communication is HTTP. That's why I'm wearing that as well. But today we are not going to talk about HTTP, so we're going to talk about events. So there's another way to communicate between two different computers. So in this way, we see everything as events. So we just pass events between computers to communicate between different systems. Okay, so in the universe of events, we see events everywhere. So just like in our universe, we see atoms everywhere. So in the universe of events, we see events everywhere. And by the way, this is not a correct depiction of an atom. Like, you have the nuclei in the middle, but the ovals and all should be something like a cloud. Okay, so this means, we just need to understand what is an event before we do anything else. So when it comes to events, you can see events everywhere. For instance, like, today, I woke up in the morning, filled the kettle, and turned it on, and then, went on to do other stuff, like, brushing my teeth, washing my face, so on and so forth. And when the kettle goes off, I just stop whatever I'm doing, and I just turn off the kettle. So here you can see the entire interaction is asynchronous. Like, I just turned on the kettle and I went on to do other stuff. So, but the reality is a bit different. For instance, the story is a bit different because, I do wake up in the morning and turn on the kettle, but I'm not interested in turning it off. So when this kettle makes this, sort of annoying noise, I don't usually respond to that noise, but my wife do. She usually complains about that as well. But for me, this noise doesn't make any sense because I don't respond to that, but my wife do, and my wife does. And then what she does is she turns off the kettle and then maybe start making tea. So here the point is, so kettle does not know who's going to receive the event. It doesn't even know the existence of other actors. Kettle just emits the event, and then whoever interested in that event can respond to that event. So that's how it works. So there are two key points you need to keep in mind. So one point is like it is asynchronous. The other point is events usually emitted by some entity, but they are not interested in who is receiving that event. So if we try to model the same thing with computers, it would look something like this. Let's say one computer is emitting the event. So let's say water is boiling. And then if you want to broadcast this event to C1 and C3, which are again different computers, let's say, you need something in the middle. So you need something to facilitate this communication between C1 and C2. So this is usually done using message brokers. They just basically broker the communication between different computers. So that means we just need to talk a bit about message brokers. So when it comes to message brokers, you need to have certain attributes to be a message broker. So one thing is when you take message brokers, you have something to represent the event. That is usually a message. And then you have topics, and then you have publishers and subscribers. Usually what happens is that publisher publishes messages through some topic, and then subscribers subscribe to some topic and receive the messages. And then these events can be persisted. So what that means is like, if the subscriber is not available, they can receive the event at a later time. And it supports retrying whenever there's a failure. These are like, usual distributed system problems. So whenever there's a transient failure, you should be able to deal with it. Message brokers also can deal with those problems. And then it supports different types of acknowledgements. Again, these are like usual distributed system problems. So you should be able to acknowledge in different ways to deal with different business requirements. It can do transactions. So one thing you need to keep in mind is when it comes to transactions, these are not usual ACID type of transactions. These are a bit different, but keep in mind that message brokers also support some form of transactions. And finally, like, you can do load balancing as well. Like if the load is too high, you can add multiple consumers, which we call competing consumers. So using competing consumers, you can do load balancing as well. So likewise, when it comes to message brokers, there are like, different attributes. And there are a bunch of implementations. Some of the popular implementations are like Kafka. Like, whenever you talk about event-driven architecture, you would usually see Kafka message broker. Then you have RabbitMQ, which actually uses AMQP transport. Then you have NATS, which is quite popular in the CNCF world. And then you have IBM MQ, which has been there for like forever, I think. And then we have ActiveMQ, which is an open source project done by Apache. And we have Amazon SQS as well. So likewise, there's a long list. And there's a little fun fact as well. Some time ago, we wanted to implement a message broker as well, and we had a message broker which we called WSO2 MB. But unfortunately, we had to sunset that product. And if you guys are interested about that product, you can talk to Ramit, Asanke B, Mariam, and there are a bunch of other people. But we learned something by doing this. What we learned is, getting this type of products right is really hard. It's not an easy job at all. So you just need to deal with a lot of things. So when you're dealing with event-driven architectures, I think the first thing is just find out the right message broker for your system. Now that we don't have WSO2 MB, we'll have to go with something else. Okay, so going back to the example of the kettle. So now we have events and we have some sense about events. But the thing is, we need to understand different types of events emitted by different systems. So for instance, if we go back to the kettle example, like kettle emitted an event, and that event is that, in noise. But I knew what that means. So similarly, computers can emit events as well. So when they do so, we need a way to make sense of it. So to describe these events, we usually use async APIs. So that is quite common in the world of event-driven architecture, and it's quite parallel to Open API specification. So if you take async API, it has like server details, it's had different channel details, and then you can see different messages associated to each channel. And then if you look at the message itself, you can see like the structure of the message, different fields of the message, and you can even see like constraints associated to these messages as well. So you can use async APIs to describe events emitted by your systems. So now others also can make sense of these events. They can just go through the async API and see what's going on, and they can decide which channels they want to subscribe to. Okay, so that's a bit about async API. So now that we have discussed all the building blocks related to event-driven architecture and how we want to solve this, now we can see what do we actually get when we do event-driven architecture. So when we do event-driven architecture, what we get is a loosely coupled system. So we get a loosely coupled system in the form of publishers, subscribers, messages, and then you have message book in the middle, which has different topics. So this is what we usually call event-driven architecture. Of course, there are many shapes of this architecture, but the core of the architecture would always look something like this. So let's talk a bit about benefits of event-driven architecture. So when it comes to benefit, there are several benefits. Like some of the key advantages or benefits are like you can do real-time processing. That means like, if you want to do a stock brokerage system or something like that, this would be a good choice. Scalability is again one of the advantages you get when you do event-driven architecture. This is again mainly because all the systems are loosely coupled. You can easily scale your system. These systems are resilient. Again, this is because these systems are loosely coupled. Just because one system is down, other systems does not have to stop working. They can just continue to work because these systems are loosely coupled. Extensibility is again an advantage of event-driven architecture. One of the reasons for that is like, one example would be like if you have a payroll processing system or whatever, and then if you want to suddenly add a monitoring system, all you have to do is like pop up the new monitoring system, subscribe to relevant events, and start monitoring the system. And it has a better resource usage as well. Like, for instance, if you are interested in the events, like you don't have to do long polling or whatever, now you directly get the event, so you can reduce the network communication, time spent on searching for the events, all those things goes away. Okay, those are some of the benefits. As many things in our universe, event-driven architecture also has different shapes. So I'm not going to talk about all the different shapes, like they have CQRS pattern, they have event sourcing, and you also have events itself, and then you have competing consumer pattern, which I explained like a few minutes ago. So likewise, there are different shapes when it comes to event-driven architecture, but I just want to quickly touch upon event sourcing because I find it quite interesting. So when it comes to event sourcing, what happens is that we collect each event as a series of logs. So what we do is we just collect all the events one after another, and then using those events, we just create the snapshot of the application state. So that's what we usually do. This is a bit different from our traditional approach. In our traditional approach, what we do is we just have a database which represents the application state. And whenever there's a new event, we just update the database tables. That is what we do. But here it's a bit different. We don't have a database table or anything like that. We just collect all the event as a series, and then by playing each event, we just generate the application state. So usually the application state is in memory. So here's something interesting. There's something interesting. Here you can see like what we have is read and write. There is no update and delete. So that means there is no mutable state, shared mutable state. So if you don't have shared mutable state, what that means is you can easily do concurrent applications. So I'll talk a bit about event sourcing when I talk about WebSub Hub. Okay, so let's talk a bit about expansion of event-driven architecture. So you guys know the core concepts. Now let's see like how we can expand event-driven architecture into different areas. So event-driven architecture is already everywhere. Like if you take e-commerce system. You can see like, Amazon, Alibaba, eBay, they all use event-driven architecture in some form. And if you look at social media platforms, needless to say, Twitter, LinkedIn, Facebook, they all use event-driven architectures. So when it comes to streaming services like Netflix, Spotify, YouTube, they also use event-driven architecture to stream different events. So when it comes to transportation and delivery, you can get different types of implementations. Uber, Lyft, UPS, they all use event-driven architecture. And I think Uber and LinkedIn is quite popular for using Kafka at a very large scale. So apart from that, if you look at it about the expansion of the event-driven architecture, so the expansion could happen in many different ways. For instance, GraphQL is becoming quite popular. So GraphQL has GraphQL subscription, which you can use to emit different types of events to the front end. And then we have HTTP server-sent events. So this is quite popular when it comes to AI-related applications because, to send back the prompt response, they use server-sent events. And WebSocket, I think you guys already know about WebSocket, so I don't have to describe about WebSocket. It's been there for like many years. And then like you have gRPC to do like internal streaming like stuff, like when you want to stream events internally, gRPC is quite popular. And then we have WebSub, which helps you to expand your event-driven architecture into World Wide Web because WebSub operates on HTTP. Okay, so I just want to talk a bit about WSO2's contribution to this expansion. So the first thing is I just want to talk a bit about Ballerina WebSub Hub module. So there are two modules. One is for the WebSub Hub itself, and the other one is for WebSub Hub subscribers. So using those modules, we actually developed a WebSub Hub, which actually can do 3 million requests per day. So this has been tested already because Mosip, which is an open source identity platform, something similar to Aadhaar, so they already use our WebSub Hub to integrate different systems. So we actually went to their conference, their very first conference. This is, by the way, Ayesh, who's there in the audience. So you can see, like, everyone is quite happy, and we are happy to see they are happy. So I would say, like, this is the only library when it comes to any language. This would be the only library in the world that can do like 3 million requests per day. I don't think other languages even have a library to do this. So this is the architecture of WebSub Hub we just implemented. So this is a typical event sourcing system. So what we do is, like, there are different types of events, like, subscribe, unsubscribe, create topic, delete topic. What we do is we collect all these events as a series to a topic in the Kafka message broker, and then we broadcast those events to all the different hubs. Then the application state is maintained in memory in each hub by responding to each event. So in the case like if the event goes down, in the case like the hub goes down, we need to reinstate the state. In order to do that, what we are doing is, like, whenever we get an event, we have a consolidator which creates snapshots of each event. So that, when the hub goes down, it can talk to the consolidator and get the latest state and continue to work without any issue. So I just want to talk a bit about Ballerina WebSocket module as well. Ballerina WebSocket module can be used to write different WebSocket services. You guys may already know. So the thing we've been working on is, like, when you write a Ballerina WebSocket service, we've been researching on automatically generating the async API from the WebSocket service. So we have done a lot of research in this area, and we actually have a experimental implementation as well. There are a few things to iron out. Once this is done, I would say, like, this is the only language where you can just write the WebSocket service and then generate the sync API automatically. And then I just want to talk a bit about Ballerina language itself. Like when it comes to Ballerina language, we have done a lot of things to support event-driven architecture. Like first thing is we can connect to different message brokers. That's one thing. There's nothing new there. But when it comes to other things like GraphQL subscription, Ballerina supports that. When it comes to HTTP server-sent events, Ballerina supports that as well. WebSocket, I just mentioned, we already support that. And when it comes to gRPC, we have a module for that. And then when it comes to WebSub, I mentioned we have a bunch of modules for that as well. So I would say this is the only language in the world that supports all of these seamlessly. So likewise, we have done our contribution to expand event-driven architecture as well. So we are quite proud about it. And that's what I wanted to cover. So those are a few things I just wanted to cover during this presentation. And hopefully, trigger some curiosity so that, you guys can contribute to this effort of, expanding event-driven architecture. So I would like to end with this quote, like, I have no special talents. I am only passionately curious. Like, if you just, this was said by Albert Einstein. Like, if you look at his biography, you will see that he was a pretty ordinary guy who did extraordinary things. So the only thing he had was curiosity. So I hope you guys would be curious about event-driven architecture and help us, collaborate, invent new things in this space. Okay, so that's all I have. If you have any questions, you can ask.
Thank you for the presentation. It was amazing. My interest was in the WebSub hub, and why. I'm trying to understand why WebSub hub needs to be in front of the Kafka. What is the objective? How can I learn more about it?
Okay, so I'll try to put it in a very simple way. So if you take Kafka, you can do event-driven stuff with Kafka itself. There's no issue at all. But this has its own protocol. Like Kafka has implemented their own protocol, and publisher and subscriber use that protocol to communicate. But when it comes to WebSub Hub, what we actually do is like we add a thin layer in front of Kafka, so that this communication between publisher and subscriber can be done using HTTP. So that means you can use the World Wide Web infrastructure. It is built for HTTP. Using that, you can do event-driven architecture. In the case of Mossip, what they do is like they have a public hub, systems outside of their network, like for instance, print shop. So whenever there's a new identity, their like government office update the topic, and event notification goes to the print shop, which is outside of their network. So that communication happens over HTTP. So they just wanted to utilize the World Wide Web infrastructure to collaborate with different systems. And if you're interested, we have our WebSub guy there, Ayesh. So we have done a couple of deployments as well. Like one is this Mossip deployment. The other one is in Choreo itself to connect Ascario and Choreo. These deployments were done by Aish. So if you're interested, you can talk to him. Any other questions? I think we are out of time. So if you guys have any questions, when I'm not working, I usually spend time at the TT table. So you guys can meet me there. Okay. Thanks.